Okay, hello class. So this is lesson 3 in Trig for grade 11. We're going to be talking about trig identities today. So this is actually not a new concept, an identity, but it's the word we just really haven't seen before. But we'll learn like what an actual identity is, and I'll try to like justify why we're doing this a little bit. This is probably the hardest lesson to justify there, and so it's a part of it. And so there's gonna be a little blurb about grade 12, but it goes beyond that. And so really what we're doing is simplifying trig expressions and also proving trig identities. So success criteria, we're going to be using these things called the Pythagorean quotient identities. We're going to learn about those. You can write equivalent expressions and then proving trig identities. So as a warm-up, we just look at this, and so this kind of like talks about reassesses that, like, if you do this, you make sure that you understand what it means to have like a ratio, so sine of an angle, cos of an angle, and then if we divide them, you'll actually notice that like as you go through, these are just random angles that aren't really related to each other. They're just in each quadrant. You just get the exact same answer for each, and so that then we actually like come up with this idea, and so we're gonna talk about it again. That tan is actually always the same as the sine divided by the cos, which maybe isn't totally a surprise. It's like from the unit circle, like we actually determined that tan was the ratio of sine divided by cos, and so we'll talk about that. But this idea of tan is sine over cos, that's what we call an identity. So it means that so you can think about tan as simplify, or sine over cos simplifies to tan. But it's what we call an identity. It's always true for everything. Equations, on the other hand, are only true for certain values. So things like 2x plus 3 is 5 is only true for x equals 1. Cos theta is 0.2345. That's only true for like some values, not all. It's true for wherever x is 0.2345 around the circle. And so we can get angles in the first quadrant, angles in the fourth quadrant, and then as we go around the circle backwards and forwards, we can get more angles, but it's not true for everything. Like, it's not true for 90 degrees. Cos of 90 is not 0.2345. Identity, on the other hand, is true for everything. And so a simple one is this. So this is why I said this isn't a new concept. X plus x is 2x is true for everything. We know it. It's the simplification of like x plus 2x is or x plus x is 2x, and so it's always true. Distributive law invites more of these. Any kind of combining like terms, any kind of simplifying invites this idea of an identity. Tan theta is sine over cos. This is an identity. It's true for everything. Every value that we can put in for theta, it's true. So this is back to the unit circle. So this is like kind of a review slide, and just like make sure that we understand this from lesson 2. The point goes around the circle. If we have a unit circle, the radius is 1. We notice that like this point has an x and y coordinate, but we also remember that sine theta is y over opposite over a hypotenuse, which is y over 1, and so sine theta is just y. Likewise, cos theta is just x, so cos theta is adjacent over hypotenuse, so it's just x over 1 or x. And tan theta is opposite over adjacent, so y over x, or it's really just the slope, rise over run. Rise over run. This is important. I'm going to come back to this because when we talk about the quotient identity, which we've already talked about, this is true in the unit circle. And in fact, all trig ratios come from the unit circle. And so the radius is always 1. Like, we don't talk about a radius when we just talk about sine theta or cos theta. But since the tan ratio is the slope and the sine is the y, or the rise, and cos is the x, then it just makes sense to say that tan is sine over cos, rise over run. That's what works. That's what makes sense. The Pythagorean identity is like, I'd ask you to like think about what does the Pythagorean theorem have to do with this. And when you look at it, you're like, well, okay, it's a right triangle. X squared plus y squared is 1 squared. So that means x squared plus y squared is 1. And that's in fact the equation of the circle. But if we use trig, like x is cos and y is sine, so then cos squared plus sine squared is 1. Or sine squared plus cos squared is 1.
Forte call 219, please. Miss Forte call 219.
Sorry about that. So then, since the point xy forms a right triangle with a radius of 1, and the sine ratio is the y value, and the cosine ratio is the x value, then x squared plus y squared is 1, or y squared plus x squared is 1. Sine squared plus cos squared is 1. I don't know why we don't write cos squared plus sine squared. It doesn't really matter. X squared plus y squared is 1 squared, which is just 1. And that's true for everything. You can try it. This is probably new to you, like the idea of squaring. We don't actually, we'll see this in one of the examples, but we don't actually show the brackets and put the square outside. We square the whole thing, which is sine times sine. The notation for it is to put the square there, and so that's just consistent with what the notation is. Okay, but since this is true, this is actually also true. If you put the cos squared, if you subtract cos squared from both sides, we can say that sine squared is 1 minus cos squared. Likewise, cos squared is 1 minus sine squared. So these are all tools that we're going to use to simplify trig expressions, but also to prove other things are true. So we know tan is sine over cos, sine squared plus cos squared is 1. We're going to prove other things are true as well. Okay, so some justification of this. In grade 12, we're actually going to use these more to solve complex trig equations. So in lesson 2, we solved some trig equations, so things like tan theta is negative 0.5. And so you can imagine in grade 12, and we won't do this in this class, but if you're just listening to me, like instead of tan theta is negative 0.5, which is something we could do here in grade 11, find the answers that make that true. In grade 12, we do like actually solving trig equations more, and so we might have something like sine theta over cos theta is negative 0.5. And so then you might get stuck on how to solve that, but if you use a trig identity, that's the same as tan theta is negative 0.5. Okay, let's look at some simplifies. Tan theta is cos theta. Tan theta times cos theta, like what is this equal to? Well, we know tan is sine over cos. And we know from our rational expressions that if we're multiplying a fraction by a whole number and the fraction denominator is the same as that whole number, then they can cancel. And so the answer is sine. And so tan theta cos theta is actually sine. And that's how you show it. That's how you show their equivalent. Similarly here, we can say that tan squared theta plus 1. So it really is this, tan theta squared. And so that's why I said like the notation just means like square tan. Well, we know tan is sine over cos. And so if we square it, we can say that's the same as sine squared over cos squared plus 1. And then with a common denominator, we can change the plus 1 to a cos squared over cos squared. That just to make the common denominator. And then in rational expressions, you keep the denominator the same and add the numerators. Now the numerators aren't like terms, so we just kind of put them beside each other. Sine squared plus cos squared. And this is all like back to our rational expression stuff earlier in the course. Sine squared plus cos squared, though, we know is 1. So it's 1 over cos squared. And so simplified, tan squared plus 1 is 1 over cos squared. But one more further step, this is the reciprocal of cos squared, which is actually, since tan squared is sine squared over cos squared, it just follows that since 1 over cos is secant, 1 over cos squared is secant squared. And that's actually a lot simpler. Tan squared plus 1 is secant squared. And what this basically means is like if you graph tan squared plus 1, like with a variable, and you graph secant squared, you get the exact same thing. It's kind of interesting.